The new AVL Simulation Suite 2025 R2 is here, and over the course of the next few minutes, we're going to take a look at some of the highlights that are inside. My name is Stephen Buscher, and together, let's explore what's inside this latest release.
The model flow diagram allows the user to easily analyze and interpret their results. Currently, we are checking the power results in the model flow diagram. If we take a look at this specific block, which is the E-motor, we have three values that correspond to this block. One is the frame value that represents the stored power in the E-motor. This means the rotational speed and its inertia. We have this thermal port, which indicates the losses of the E-motor, and we have the connections, which represent how much power is flowing from one to the other component. The values for the connections, frames and ports can be easily disabled or enabled with the checkboxes on the left side of the screen, and it allows to view the results for different domains. If we go to the cooling subsystem, we will see a similar plot, only the domain here is liquid and mechanical. If we disable the liquid connections, those disappear on the diagram. Now we will check the air conditioning domain, where we can see the combination of the gas domain, AC domain, thermal domain, and liquid domain interacting together. The model flow diagram also works with the animation, so you can see the results, and you can also see the values at specific simulation times. The Discretized Solid Cylinder 3D component allows you to define a three-dimensional grid of solid wall cells of a cylindrical shape. It is a heat accumulating body and can therefore be used in building an engine structure thermal network, making it especially suitable for modelling battery pack cooling systems. If we open the Discretized Solid Cylinder component properties, we can see the following. The type of geometry, which can be full cylindrical, half or quarter cylindrical. The material, which can be a single material or multiple layered materials. The cell sizes, which can be constant or variable. The number of cells, and whether the cylinder is hollow or full. On the bottom, we have the heat ports table, where the user defines the direction of heat flow, and measurements point table, where the user can select the cells where he wants to measure the temperature. The model you see on your screen investigates how effectively the cooling system dissipates the generated heat if a heat source is placed at the edge of one of the cylindrical battery cells. After we run the simulation, we notice some interesting results. The 3D visualization of temperature distributions between the discretized cells. If we run the animation, we can also observe how the temperature distribution changes over time. Temperature changes over time curves for specific discretized cells. The purpose behind this feature is to enable accurate modelling of advanced lithium-ion battery designs that use blended electrode materials like LMFP, which combines the thermal stability of LFP with the energy density of LMP. Traditional P2D models fall short here, as blends behave non-linearly. To address this, CRUISE M introduces a refactored electrochemical battery component that supports material-specific inputs for cathode, anode, separator, and electrolyte. Users can configure blends across entire electrodes or specific layers with individual settings for intercalation and degradation. CRUISE M ensures consistent initial conditions by automatically determining stoichiometries that match border potentials and SOC. A new installation model highlights the non-linear pseudo-OCV behavior in graphite silicon blends, and ECB input pages in pouch and cylindrical cell components have been updated accordingly. The PEM Electrolyzer System Generator is accessible from the Wizards and Generators tab in the Efficiency ribbon of the CRUISE M Home tab. We navigate to the Generators tab and locate the PEM-L System Generator, opening it by pressing the Start button in its description window. The PEM-L Generator window will open. The main input parameter needed for the generator to build a PEM electrolyzer system model is hydrogen production power, which basically dictates how much hydrogen is produced during the electrolysis. Let's say that we would like to create a 100 kilowatt equivalent of hydrogen. Besides the main input parameter, users can also alter the otherwise predefined advanced model settings, such as the compressor efficiency, AC-DC efficiency, stack current density, and voltage at that current density, and other parameters. Based on the main input parameters and advanced model settings, Generator calculates the system performance KPIs and plots the system power Sankey diagram generated on the right side of the PEM-L generator window. Once the desired values of the system performance parameters are reached, we can click on the Finish button. After a few moments, the system topology is created. The created electrolyzer system can be divided into 5 subsystems. First, it's a PEM-L electrolyzer stack. Then, there is an anode side balance of plant, a cathode side balance of plant, a current source, and control elements. The Combustion Analysis Wizard can be accessed through a combustion chamber component. The calculation is done based on the geometry data of the cylinder and operation conditions of each individual operating point, like engine speed, performance, and mass flows. As a result, it is possible to extract the rate of heat release and other KPIs. It is possible to trigger combustion analysis for different operating points, and looking into the energy balance together with all other KPIs summarized in the summary table for each operating point. After finishing the Combustion Analysis Wizard, the rate of heat release curves are transferred into the combustion model itself. One new feature is that we are also able to import operating points directly from the iFile. It is possible to take measurement files and connecting each individual quantity, like engine speed, performance, fuel and air mass flows, together with correct units and transferring them to individual operating points. With that, the Combustion Analysis Wizard is a starting point to analyze measurement data and create a rate of heat release table for combustion to ideally reflect what is happening on the engine testbed.
If you want to discover more about the AVL Simulation Suite 2025 R2, why not visit our website or follow the link below. Here, you'll find more information about the features and contents inside this release. See you next time.